Having set up the basics of what a game is, we can now start actually thinking about the strategic analysis of a game. Let's look at this very simple 2x2 normal form game. Now, typically, the strategy that you're going to want to play is going to depend on what you believe the other player is going to want to do. That was the whole point of introducing the idea of a belief. Now let's look at player 1's options here. Player 1 could play up or down, player 2 can play left and right. Is there anything player 1 could believe about what player 2 is going to do that would make down a sensible choice? In other words, would player 1 ever want to play down for any beliefs about what player 2 is going to do? Let's take a look. Let's suppose player 1 believes that player 2 is going to play left. Then, well, up gives him a payoff of 2, down gives him a payoff of 1, so he'd be better off playing up. If he thinks player 2 is going to play right, he's still better off playing up. In other words, no matter what player 2 does, whether he plays left, right, or whether even if player 1 has some probabilistic beliefs that with only probability p he's going to be playing left, and with some probability 1 minus p he's going to play right, it doesn't matter. Up is always a better choice than down. He's always going to get a higher payoff from up than he's going to get from down. So in other words, there's no belief player 1 could have that would make down a good choice. So we say that up dominates down. This idea of one strategy dominating another, in other words, one strategy giving you a higher payoff than another, no matter what your opponents do, is one of the basic ideas in strategic analysis. Now, let's look at this idea of domination a little more carefully. Does there always exist a domination relation between strategies? Well, what about player 2? Does one of player 2's strategies dominate the other? So does L dominate R, or does R dominate L? The answer is no. Neither of these strategies dominates the other. Notice that if player 1 plays up, L is better than R. If player 1 plays down, R is better than L. So in this case, player 2 does not have a dominant strategy, but player 1 does. Dominance doesn't necessarily have to be at the hands of another pure strategy. So you can even have dominance by a mixed strategy. So let's look at this other example. Notice that none of the three strategies dominate one another. So up doesn't dominate middle, middle doesn't dominate down, and down doesn't dominate up, nor vice versa. So all three of these strategies are independent of one another. However, remember the idea of a mixed strategy. Player 1 could decide that they're going to flip a coin between playing up and middle. So they're going to play up with probability 1/2 and middle with probability 1/2. So why don't we just write another row for this mixed strategy? So this is the coin strategy. Well, if they flip a coin and player 2 plays left, well, with probability 1/2, they're going to get 4. With probability 1/2, they're going to get 0. So their payoff from flipping the coin is going to be, the expected payoff is 1/2 times 4 plus 1/2 times 0, which is 2. Player 2 will get 1/2 times 1, 1/2 times 0, so it's 1/2. If they flip the coin and player 2 plays R, player 1 is going to get 1/2 times 0 plus 1/2 times 4. Again, it's 2, and player 2 is going to get 1. Now we can see that this flip a coin strategy, flip a coin between up and middle, it dominates down. You get, no matter what player 2 does, player 1 gets a payoff of 2. versus getting a payoff of 1. So flipping a coin between U and M dominates D. In other words, you can have dominance by a mixed strategy, not just a pure strategy. So in particular, you can have a pure strategy that is not dominated by any other pure strategy, but it is dominated by some mixed strategy. Let's write down a proper definition of domination. Take a strategy SI in the set of all strategies for player I is dominated if there's a mixed strategy sigma I such that no matter what the other players do, so for every possible strategy profile for everybody else, if we look at the utility that the player I gets from playing this mixed strategy sigma I, it's greater than, so it's strictly higher than what his utility would be should he play the strategy SI. In this case, we say that sigma I dominates SI. It's important to note here that we're talking about strict inequality rather than a weak inequality. So the player has to be strictly better off with the mixed strategy sigma I than with the pure strategy SI. A very, very basic behavioral theory is that players don't play dominated strategies. So why would you ever pick SI if you could do sigma I and no matter what others do, be better off? So again, this basic behavioral theory says that nobody is going to play a dominated strategy. Let's denote by undominated sub I, so UD subscript I, the subset of strategies such that is the set of all strategies that are not dominated. To write this down a little more carefully with mathematical notation, we would write it down like this. So UDI is a set of all strategies little si in capital SI such that there is no mixed strategy sigma I that dominates SI. Just the theory that players don't play dominated strategies is sometimes enough to fully understand what's happening in a given game. Let's take the classical prisoner's dilemma game. The story goes as follows. You've got two people who have committed a crime. They've agreed beforehand that they will not, if they get arrested, that they won't tell on each other. So if they stick to this original agreement, so if they cooperate with one another, then they both get a relatively mild sentence. On the other hand, if they both testify against one another, so if they defect from the agreement that they had originally made and they both defect, they get a relatively harsh sentence compared to when they both keep their mouths shut. On the other hand, if one of them sticks to the original agreement and cooperates with their friend, but the other person says, actually, I'm going to defect from this agreement, then the person defecting gets no punishment at all, but the person who cooperated gets the harshest punishment. So that's the story behind Prisoner's Dilemma. And the idea of players don't play dominated strategies is enough to fully understand what's going to happen in this game. From each player's perspective, there is a dominant strategy. If player 2 is going to cooperate, then and I'm player 1, I'm better off to defect. I get 3 instead of 2. If player 2 is going to defect, then I'm also better off to defect. I get 1 instead of 0. So D dominates C. The game is symmetric, so D dominates C for player 2 as well. 3 beats 2, 1 beats 0. So the only option here is for players to play D-D. So in this game, we should expect the outcome to be that they both defect from their original agreement and they get the relatively harsh punishment. They would both actually have been better off cooperating because they could have gotten a payoff of 2 each instead of getting 1 each. We use the idea of Pareto Improvement. CC is a Pareto Improvement over DD because both players are better off under CC than under DD. So this is an example where there's a tension between individual incentives. So each player individually has an incentive to play D rather than C because it's a dominant strategy. Yet efficiency tells us that, so Pareto efficiency says that the outcome should be one which is not, which can't be Pareto improved. So CC would be a Pareto efficient outcome, and DD is a Pareto inefficient outcome. Yet we see that the outcome is going to be DD when each person looks out for themselves. So there's a tension here between the strategic incentives and what's efficient. So using only this theory that players don't play dominated strategies, we're able to demonstrate the tension between Pareto efficiency and individual incentives.